This is a demo of the horizon cube, and we're going to apply the horizon cube on a tertiary sequence in the Dutch offshore. The sequence is marked by the green and yellow horizons, which are conventionally mapped horizons. The dataset is from F3. It's about 380 square kilometers, and as I said, offshore the Netherlands. The first thing we did is to calculate a steering cube, and the result of the dip steering cube is seen here, where it's dipping to the left, it's displayed in blue, dipping to the right, displayed in red. And this is the basic input for our horizon tracker, and after application of the horizon tracker we have generated hundreds of horizons purely by following the dip. These horizons, they may divert, in which case if the holes becomes too big we are inserting new horizons, but they may also converge together. As you can see along here, all these horizons, they divert off, merge together along this unconformity. The only thing that these horizons cannot do is they cannot cross each other. This is a continuous horizon cube, meaning that the horizons are present everywhere. To the left we also see that horizons merge together along this condensed section. Now once we have calculated the horizon cube, the fun part starts, because now we can do all kind of geologic interpretations, and we'll demonstrate this by just looking at a couple of lines. And let's first have a look on how the depositional sequence actually filled in this sequence. And we're doing that by playing with this slider here. The slider allows us to peel off geologic timelines and to add them. So basically what we're doing is now we're moving through geologic time, and you can see the horizons or the sediments being filled in from the right hand corner. And as we move our slider we see that we get different kind of stacking pattern, different sedimentation patterns emerging as we move through geologic time. So basically each of these horizons in the horizon cube has been given a unique identifier that links the horizon to geologic time, that is relative geologic time. And just by playing with the slider we get already a reasonable idea of what is going on in this particular sequence. Now if we want to go one step further and we want to actually do a sequence stratigraphic analysis, we will basically do that like this. Go back to our line here, and we will use these horizons and flatten them, so we're doing a Wheeler transformation. Here we see the horizons in both domains, and this is not very interesting yet, because the lower section is continuous. This is the flattened seismic, and if I overlay the continuous horizon cube, then I don't see the nice cyclic patterns that I would like to see. So I'm first going to change my display slightly, and I'm going to truncate my horizons if they move, if they are coming too close together. And if I do that, we start to see cyclic patterns in the horizon cube. We see sediments moving first towards the right, that is the land side, then towards the land, that is the marine side, then back towards the land. We see gaps in the data where the horizons have become very dense, they were cut. This is an unconformity, a hiatus in the data, and also where they came together in this condensed section, they have been cut out. Now to do an actual sequence stratigraphic interpretation, I'm opening this module here, that is my sequence stratigraphic interpretation system, or SIS. You have to imagine that this interpretation column is completely empty when I start my interpretation, and the interpretation basically goes like this. I'm moving my slider again up through my sequences, and I'm looking at both the structural domain in the upper scene and in the lower scene in the Wheeler domain until I see a break in the data. Where I see a break, I insert a boundary in my interpretation column, and next I assign what I think as an interpreter that this particular sequence is. In this case, the interpreter called this a transgressive systems tract. Now, because the interpreter calls this a transgression, the system knows there must be a maximum flooding surface on top, and it knows that the base level must be rising. So as I'm building up my interpretation, I'm also reconstructing my base level curve. I'm getting all the important points, boundaries in the sequence marked, like this is the sequence boundary, this is the maximum flooding surface, end of the transgression, and so on. Each of these bounding surfaces, the maximum flooding surface, the top high stand, the sequence boundary, and so on, I can save as normal horizons in my system for follow-up work. The end result of such an interpretation may look like this. In this particular case, we started off with a transgression, then we had a high stand, then we had a falling stage, then a low stand, high stand, and so on. Now, the most important interval within this sequence is actually this falling stage, the blue interval here. We see some higher amplitudes, and we see that these amplitudes have been maybe slumped down the slope as the base level fell. And these could be potential targets, so it would be worth mapping these. And mapping these I'm doing again with the help of the horizon cube. So let's go back to my horizon cube and let's position my horizons such that I'm mapping out one of these bodies. So let me position one at the top of one of these slumps and also at the base of one of these slumps. So maybe something like this. Now, once I know that this is marking the top and the base, what I can do is I can automatically calculate the isopac thickness from these two horizons, and then I can set a cutoff value that identifies the boundary of my body. And in this case, the body that has been mapped like this is looking like this 3D shape, and in this way I can very quickly isolate all the slumped 3D bodies that are my potential reservoir bodies in 3 dimensions. Now, that is one application that we have now seen of the horizon cube, actually doing a sequence stratigraphic analysis and isolating these bodies of interest. Another application is actually geologic model building, and for this we are going to look at the wells that we have. In this case we have 4 wells, and what you're seeing here is the gamma ray log response. And what we did here is we used these gamma ray logs and we interpolated these along the existing horizon cube. And what you get then is a gamma ray volume that is really consistent with the seismic reflection patterns almost everywhere. Now, I can do that with any log, of course. I can do it therefore also with impedances, build my low frequency model and come up with a low frequency model that is consistent with my seismic, and therefore I'm also getting a much better, more consistent end result of a seismic inversion. This is the inverted seismic data, acoustic impedance. And then of course I can follow up and do some rock property predictions from the impedances in OpenDTEC. You can either do that within the open source part using cross-plotting techniques and probability density functions, or you can use it as we've done here using neural networks, training the neural network along the well tracks to convert the impedances to porosities. So this is another application of the horizon cube that we have now seen, and that is in geologic model building and in inversion. Let us now look at yet another application of the horizon cube, and that is in well correlation. So we have constructed here through the 4 wells a random line. And then we started a new application called the Well Correlation panel, and in that Well Correlation panel I have displayed again the gamma ray, I've displayed the Marcus, the stratigraphy. I have now the seismic as a backdrop. I've got a couple of mapped horizons, and again I have my horizon cube to help me correlating how do I get in a consistent way from, for example, this marker here to the same marker in this well log, and to here, and so on. Now, given the setting that we are looking at here, this is a pretty difficult exercise if you're not using any seismic to guide you. Now, this is more than just a visualization tool and a QC tool. It's actually a tool that can help you to update the markers and pick them in a consistent way. Let's look at this marker here, which has been picked in this well log break in the gamma ray. If we follow it, then we really would have liked to pick it here, but somebody made a mistake, picked it way too high. I can now go in and repick this marker such that I again have a consistent set of markers, and again my horizon cube is helping me to do this.